Okay, so now we need to move on to some more data that suggested that light in certain experiments needs to be considered as particles instead of waves. And so this particular experiment that was done again around the turn of the 20th century were experiments called the photoelectric effect. So I need to talk a little bit about what this effect is, and then I'll explain how that data suggested that light is probably not always best explained by waves, but sometimes is better explained as assuming that it's in particle form. Okay, so what the photoelectric effect is, it's where you have some kind of light, we're going to call it incident light here, and it's striking a metal. So what I have here is when the light strikes the metal, what will happen is sometimes if the light has the right properties, that it will knock an electron off the metal and the electron will go flying into the space. So now what's interesting is that the only way light can knock an electron off the metal so it goes flying into space is if the light has enough energy to do so. And so let's say you have a lot of energy associated with this light and it's striking the metal. Some of this energy is going to be needed to sort of loosen up the electron from the metal. This energy required to loosen up the electron from the metal is called the binding energy of the electron to the metal. However, if you have total more energy in the instant light than you have in the binding energy, any extra energy that the electron was hit with will now go into the kinetic energy of the electron that when it flies off that metal surface. And so in the end, basically what you have is that the total energy of the light that is striking that electron that's bound to the metal will be used to loosen up that electron from the metal, the binding energy, and then any extra energy that that electron flies off with, that would be the kinetic energy. And so you can write an equation there that the total energy of the light that is striking the metal is going to be equal to any of the energy needed to loosen up the electron from the metal, the binding energy, plus any energy that is found in the electron when it's flying off the metal. This would be the kinetic energy. Now what you can do is you can sort of change that equation a little bit. And so what I've done is for the binding energy of the electron, I put in a Greek letter there that represents that. The Greek letter is psi, and sometimes this is also referred to as the work function of the metal. And again, all that is just the energy required to loosen up the electron from the metal. Then what I've done is I changed the kinetic energy of the electron to the formula, which is 1/2 mv squared. So how does the photoelectric effect suggest that light is best explained as being found in particles in these kinds of experiments? Well, the reason is because the photoelectric effect could not be explained well by the laws of classical mechanics, which suggested that light was only to be found in waves. And so in particular, the prediction from classical mechanics was this: if you take some kind of metal, and it doesn't matter what wavelength or frequency of the light you use. You could use red light, you could use yellow light, you could use blue light. It didn't matter what the wavelength or the frequency of the light striking the metal. The theory from classical mechanics is if you had the light of enough intensity striking the metal, that would be able to knock electrons off the surface of the metal and they would go flying into space. In fact, when they did experiments looking into this, they did not find that. Instead, what they found was that whether you got electrons flying off into space from the surface of the metal did depend on the wavelength or the frequency of the light. So for example, here what you can see is that if we were looking at the metal cesium, if you were to expose it to red light, which here in this example has a wavelength of 700 nanometers and it corresponds to a certain frequency, that if cesium was exposed to red light, you would find that no electrons would be released from the surface of metal, so there would be no photoelectric effect. However, if you took that same cesium metal and exposed it to green light with a wavelength of 550 nanometers, you would find that electrons are going to be released off the surface of the metal, and that they go off with a particular kinetic energy. And you could actually measure the velocity which the electrons are going off. And so in that particular example, the velocity is 2.96 times 10 to the 5 meters per second. Now, if you exposed the cesium to a lower wavelength, say violet, which is a much higher frequency, the electrons fly off, but they're flying off at a much faster velocity. So that indicates that when you increase the frequency of the light going from red to green to violet, you cause the electron to go off with a greater kinetic energy, as indicated by the higher velocity that the electron is going. So again, this was not predicted by the laws of classical mechanics. And so what this was more consistent with was the idea that light could be found in particles, and that each of these particles have a certain energy, and this energy was going to be dependent on the frequency of the light. And so we already kind of talked about this. We already found some data previously that suggested that energy is equal to Planck's constant times the frequency. And so again, this rule, E is equal to H times nu, energy is equal to Planck's constant times frequency, best explains this data, in that when you have the right frequency of light, anything below 600 nanometers in wavelength, which corresponds to a certain frequency, then that will be enough energy to knock the electron off the surface of the metal. And if you just use higher frequency or lower wavelength light, that excess energy from that higher frequency will just go increase the speed of the electron. Again, I'm just kind of recapitulating here that increasing the intensity of the light does not increase the kinetic energy of the ejected electron. That was predicted from classical mechanics, but instead increasing the frequency of the light does. And the reason is because energy of a photon is directly proportional to its frequency. I just kind of mentioned that red light does not have the frequency enough to give it energy to knock off the electron, but green and violet light do. And so again, I'm going to go back to these equations here, that the total energy of the light is going to be used to loosen up the electron from the surface of the metal. That would be the binding energy which the electron is held by in the metal, plus any kinetic energy the electron leaves with. We can sort of rewrite the total energy using the relationship that the energy of a photon is equal to the Planck's constant times the frequency of the photon. So I've just replaced there the total of energy light, or energy of light, now to be equal to Planck's constant times the frequency of the light. That will be the total energy of the light. And that energy, again, will be equal to any energy needed to loosen up the electron from the surface of the metal, which is the binding energy, plus any extra energy that the electron goes off with, which is the kinetic energy. And so there I've just written the equation so that the binding energy is now represented by the Greek letter psi. You can also call the binding energy of the electron as the threshold energy of the electron, or also it's known as the work function. And then again, I'm sort of replacing the kinetic energy of the electron there with a formula which is 1/2 mass times the velocity of the electron squared. Okay, so let's go ahead and try some problems here. It says, what is the minimum frequency and the corresponding wavelength in nanometers needed to remove an electron from the surface of chromium metal if chromium metal has a binding energy of 7.2 times 10 to the negative 19 joules? What we're trying to do is figure out what is the minimum frequency needed to hit the surface of this metal, this chromium metal, with, such that we can just loosen up the electron off the metal and it doesn't fly off. So what we're going to do is just kind of reflect on what the equation we use for this is, for the photoelectric effect. So remember that total energy of the light is going to be equal to the binding energy of the electron plus the kinetic energy of the electron. Okay, so the question is, at this point, can we simplify this equation any further? And the answer is yes, because what we're trying to do is try to find the minimal amount of energy needed to apply enough energy such that the electron is loosened off the surface of the metal, which is the binding energy, and that's it. We don't want to have any more energy that could be used as kinetic energy for the electron that's flying off. So what we can do is we can set the kinetic energy of the electron in this problem to 0. So what we're going to do is write here, this is 0 here. And so what we can write is the total energy of the light is equal to the binding energy of the electron. Okay, so now what we're trying to do is we're trying to find what is the frequency of this light here that satisfies the needed binding energy to loosen up the electron from the surface of the metal. And so here, what we can recall here is that the total energy of the light, we can just think of it as E as we want, if we want, and this is going to be equal to H times the frequency of the light. So let me rewrite this equation again. So it's going to be H times frequency of the light is going to be equal to the binding energy of the electron. Okay? And so what you can do now, it looks like what we're going to have to do is find what the minimum frequency is. So we have to find nu here. So I'm going to solve this for nu. So the frequency of the light is equal to the binding energy of the electron divided by Planck's constant. And so at this point, I think we can just substitute in numbers into this equation that we have and get the answer. So let's go ahead and see where that takes us. So the frequency of the light is equal to the binding energy of the electron. So the binding of the energy of the electron, it looks to be 7.2 times 10 to the negative 19 joules. Yes, 7.2 times 10 to the negative 19 joules. And then what we have to do is divide by Planck's constant, which will be given to you on a test. So it's 6.626 times 10 to the negative 34 joules per second. And so what you can do is you can cancel out joules here. And so we have seconds in the denominator of a fraction that's in the denominator of another fraction. And so that's going to put seconds in the numerator. Actually, let me repeat that. I need to be a little more careful here. My mistake here was it should be joules per second. There, that's better. There we go. So now we have seconds, and that's in the denominator. And so that's what we want, because frequency is in per second. And so if you take 7.2 times 10 to the negative 19 and divide by 6.626 times 10 to the negative 34, you should get that answer, which is equal to 1.09 times 10 to the 15 per second, which is going to be equal to 1.09 times 10 to the 15 hertz. Okay. And then also, I think in this problem, do we have to find a wavelength associated with this frequency? So that's not so bad, so I'll just do this over here. So you remember that the speed of light c is equal to the wavelength lambda of the light times the frequency nu. And so what we can do is we can solve this for wavelength. Lambda is equal to, it's going to be c over frequency. So you can take 3.00 times 10 to the 8 meters per second and divide by frequency, which is going to be 1.09 times 10 to the 15 per second. And so what you can see at this point is that per seconds cancel out, and you'll get an answer in meters. And so you'll have to convert this to nanometers. And so there are a number of things you can do, but the thing I'm going to do here is just you take the number you get and then you convert this into nanometers. And so what I recall is that 1 nanometer is going to be, you're going to find 1 times 10 to the negative 9 meters in it. So I'm going to write 1 nanometer over 1 times 10 to the negative 9 meters. And so this, when you go about doing this, the answer should be 275 nanometers. Okay, so let's move on to another problem. So the next problem is Given the threshold energy of copper, calculate the kinetic energy in joules of an electron that is emitted when electromagnetic radiation with a wavelength of 161 nanometers is shown on the surface. Okay, again, what we're going to do is we're going to use that equation for the photoelectric effect, which is that the total energy of the light is equal to the binding energy of the electron plus the kinetic energy of the electron. Okay, so now the example we're working with now is a different metal, which is copper. And copper, because it's a different metal, will have a different amount of binding energy associated with it, say, compared to the last metal that we worked with chromium. Now we're given here the binding energy of the electron. So the threshold energy is the same thing as the binding energy. It's going to be 7.53 times 10 to the negative 19 joules. And now we're trying to calculate the kinetic energy of the electron that flies off. How much kinetic energy will have if it's being struck by light of that particular wavelength, which is 161 nanometers. And so how would we do that? Okay, so again, we're trying to find the kinetic energy of the electron given the binding energy of the electron, and if we can figure out what the total energy of the light is. And so let's kind of work on that. So total energy of the light, so you might remember the total energy of the light, we can think of it as just E, and so E is equal to h nu of the light. So I'm just going to write here for total energy of light, this is E, so I can write h nu of the light is equal to binding energy of the electron plus the kinetic energy of the electron. Okay, so the problem is we don't have the frequency of the light. Instead, we have the wavelength of the light. That's not actually so bad, because what we can do is we can figure out what h times nu is and just change this into wavelength using c is equal to lambda nu. So c is equal to lambda nu, and what we're going to do is solve this for frequency. Nu is equal to c over lambda. And now we can substitute c over lambda into nu. So it's h c over lambda of the light is equal to the binding energy of the electron plus the kinetic energy of the electron. Okay, so at this point, again, in this problem, we're trying to figure out what the kinetic energy of the electron is, given we know what the binding energy is, and we also know what the wavelength of the light is that is hitting on the surface. And so what you want to do is you want to solve for kinetic energy. So kinetic energy should be, of the electron, should be equal to, it looks to me, we're going to subtract binding energy of the electron from both sides of the equation. So it should be equal to h over c over the wavelength of light minus the binding energy of the electron. Okay. So I think at this point we can just sort of plug in numbers and see what the kinetic energy of the electron is. So we'll work that out. So the kinetic energy of the electron is equal to h, which is Planck's constant 6.626 times 10 to the negative 34 joules per second. C, which is 3.00 times 10 to the 8 meters per second over the wavelength of light. So we have 161 nanometers. Now you can see there's a problem here in that what we have to do is we have to convert nanometers to meters, and you can do this within the problem like this. So you times 1 times 10 to the negative 9 meters over 1 nanometer. This will work. So this should be this term here. And then you subtract from this the binding energy of the electron. So the binding energy of the electron is going to be 7.53 times 10 to the negative 19 joules. So let's go back to this term, which is h times the speed of light times the wavelength of the light in meters, and let's make sure things cancel out here. We hopefully will get just joules that we can subtract another joules from and get an answer for the kinetic energy in joules. So I'm going to, let's see, we have seconds here in the numerator, cancels out with seconds in the denominator here. Nanometers cancels out here, meters cancels out here, and so what we have is joules, a number in joules minus another number in joules, and that hopefully will give us the correct kinetic energy. And I think if you work out the math, what you'll find, the kinetic energy of this electron should be 4.82 times 10 to the negative 19 joules. And so that should be the answer there. Okay, and that's it. And we will see you next time. Thank you for listening.